Young's modulus for all of our materials, in this case the A36 steel, 200 gigapascals. Yield stress, like we saw in the previous problem, 250 megapascals for steel. We do have two different cross-sectional areas. The diameter from A to B is 50 millimeters. From B to C is 25 millimeters. Length AB, 0.6 meters. BC is also 0.6. We're applying a load P of 200 kilonewtons. And the one other given piece of information that we're going to have to use is that initially, before it's loaded, there's that 0.15 millimeter gap between C and D. I'm going to call that just delta in the given. 0.15 millimeters. And we want to find here, after it's loaded, what's the wall reaction at A and what's the wall reaction at D. All right, questions so far on what we're looking at here? We have all one material, but the cross-sectional area changes between AB and BC. Also, the internal force changes between AB and BC. For our free body diagrams, then, we're going to need how many sections to solve this one? First section, if I make a cut through this area here and take everything to the left-hand side, I'm keeping the wall reaction in this picture. So I have the wall reaction on the left-hand side, and where I cut through it, I will have the internal force in section AB. Now the assumption that we're going to make here, and then we're going to verify at the end, is that when we apply this load here, is we're going to bridge this gap, and then point C and point D will be touching each other. So it's going to bang up against the wall when we apply this force P to it. When we do that, what do we know about, well, let's start at A. The force at A, because it's bolted into the wall can either push or pull on the object at A, because we can't pull it away from the wall and we can't push it into the wall. The wall resists us pushing it and the bolts resist us pulling it. However, at D, we have to think about the constraint there. We can't push it into the wall because at D there's the wall there. But we could, in the absence of all other constraints, pull it away from the wall. So what we know at D is that the wall can only push on it at D, but the wall at A can push or pull. I'm going to draw it to the right, but this could turn out to be a negative sign. Or we could get a negative value for A, and that would be OK. But at D, because the wall can only push there, the assumption that D pushes on the object has to be correct, and we'll see that at the end. My intro cut in AB, I now do the same thing through BC. I can, again, take everything to the left-hand side. Whatever direction I assume for A here, I just copy it exactly here. I have that applied load at B of 200 kilonewtons. Oftentimes, this will be enough to solve the problem, but looking at what we're asked to find, we need the force at A from the wall and the force at D from the wall. The way that I drew the free body diagrams here, I don't have a picture that has it doesn't have D in it. I only have A and my two internal forces. Therefore, I need a picture so that I can see what the force is in the wall at D that has it. So my last picture, assuming it bridges the gap, the wall at D will push on my object. I'm assuming that the wall at A pushes on my object. And in this picture, I have my applied load of 200 kilonewtons. So I have two internal pictures. And I have this external picture. And I need this really only so I can find out what D is. If I didn't need to know what D is, if I just wanted to know the stresses, these two pictures would be enough for that. Here, we don't because we're not taking a moment or anything. We're just doing forces in one direction. These will come into play when we do the DIL equations. So for here, it's OK as long as I have them listed over there. It probably would help if I kind of marked these points maybe. That way I would know. But for the free body diagram, most importantly are going to be the forces and those internal cuts. Each free body diagram gives us one equilibrium equation. For later steps, this is going to be useful for the simultaneous equations. Right away, I'm going to get my internal forces in terms of A in preparation for that step. Where this is going to help is when I make those substitutions in the DIL step, I'll be able to replace those two internal forces both with A, and it's going to reduce the number of unknowns I have in that equation. We wouldn't have to do this now, but it's going to help us later on. Right, that's our equilibrium step. Compatibility, this is where we have to be a little bit careful. How will our compatibility, how will the deformations of the sections relate for this problem? We assumed that it bridges that gap. So if we add how much AB stretches or contracts, and we add up how much BC stretches or contracts, that has to add up to, it has to fill that gap in. So unlike the example we looked at on Tuesday where it was already between two fixed ends, and we knew that the total deformation had to be 0 since it couldn't grow or shrink, here we're saying it grows exactly the gap size. So basically it hits that wall, and then it might want to keep getting bigger, but it can't because the wall is there. So our compatibility is going to be that delta AB plus delta BC is equal to that gap of 0.15 times 10 to the negative 3. The deformation to internal loads. Once again, we have no thermal component to this, just the mechanical component. The deformation in AB is going to be PAB. I can right away do that substitution as negative A. Times the length of AB is 0.6. Divide by E. Divide by A. For section AB, it has a diameter of 50 millimeters. For the deformation of section BC, it will be PBC. I'll make that substitution right away and put it in terms of A, times its length of 0.6 over 200 gigapascals times pi over 4 times 25 millimeters squared. The stress in section AB is P over A, its internal force over its cross-sectional area, and BC, its internal force over its cross-sectional area. But once again, in this equation, 7 and 8 we can come back to at the end. We really have to use 1 through 6 to get the primary answer that we want. What are those internal forces using, or what are really A and D we're mostly interested in? So if we can find A, we can then find D, and then we can solve what we were asked to find. We look at equation 6. A is the only unknown on the right-hand side. In equation 5, A is the only unknown on the right-hand side. If we put equation 6 and equation 5 into equation 4, this one equation will now only have A as an unknown. So we put 5 and 6 into 4, And that will tell us the value of A. Solving for A, we get negative 180 kilonewtons, which means the assumption that the wall at A pushes on the object was wrong if you go back to the free body diagrams. But that's okay because at A, it's bolted to the wall, so the bolts will prevent it from moving left or right. So that force could be to the right or it could be to the left. The negative 180 is all right, our assumption was wrong. But if we now put this into equation 3, this is where that assumption comes into play that it did bridge the gap, meaning that the force at D must be positive. The force at D, we get positive 20.4 kilonewtons. We have A, we have D. We've answered the main question, what is the external force A, the external force at D? Along the way, though, we can find PAB is positive 180 kilonewtons. And PBC is a negative 20.4 kilonewtons. Now, using 7 and 8, we can find the stresses in those two. So the stress in AB, 91 megapascals in tension. The 180 divided by its cross-sectional area. Calculate the stress in BC, negative 20.4 kilonewtons divided by its cross-sectional area. The stress in BC is a negative 41 megapascals, and that's in compression. So we have numbers for everything now. We want to verify the assumptions that we made while calculating this. The first big one is, was D greater than 0? And we already covered that it was. If D were not greater than 0, our assumption that it closed the gap would not be correct, because it would mean that the wall had to pull on the system here to get it to close the gap, but the wall could only push. So that assumption had to be true to use the compatibility and to use that equation 3 in the equilibrium. Right? The other assumption that we're making is that we are operating in the linear elastic region. Therefore, were the stresses in AB and the stresses in BC less than the yield strength? In AB, we're at tension of 91 megapascals. In BC, we're at compression of 41 megapascals. The yield strength for the steel in tension or compression, 250 megapascals. Both of them are below the yield stress. So that means that we could use the DIL equations 5 and 6, that those were fair to use because we are operating in the linear elastic region.